All right, let's talk about polynomial long division. Now, many of you know what's called synthetic division, and what that does is that highlights different steps within long division to make a quicker process for finding the right answer. I personally don't like using synthetic division for the simple reason that I make sign errors, and any way that I can find to avoid sign errors is a good strategy for me. So let's go ahead and let's talk about what happens with long division of just numbers before we talk about long division with polynomials. So let's imagine that we're dividing 11 into 1437. Now, you guys could definitely do this, but let's just talk about the process or procedure that we're doing. So we're trying to figure out how many times 11 divides into 1437. Now, what we do is we take the bits that we need in order for 11 to fit into it, and then we go from there. So, for example, 11 goes into 14 one time. Now, if you notice, there's two extra places. So, subtly there's 2 zeros here. We're going to replace those with numbers. So if we looked at that and we took 100 and multiplied it by 11, that would be 1100. We would take 1100 out from 1400. So that's what we do, but we drop the zeros rather conveniently so that we don't have to write that much more. So then if we look at this, we got 1 times 11. So we write down 11 and we subtract that value. And we have 14 minus 11, that's 3. So that means that when we do all this, what's left over is a 3, and technically that's a 300. Next, we bring down the next number, and we check, yes, 11 does go into 33 at least once. In fact, it goes into it 3 times. So then 3 times 11 is 33. We subtract that off, we're left with 0. We go down, we have a 7 as our remainder, and we notice that 11 doesn't go into 7. 11's too big for that, so we put a 0 down, and we have a remainder of 7. Now, what does that actually tell us? That tells us that if I take 1437 and divide it by 11, I will have 130 plus 7 11ths. All right? And so that's how the long division algorithm works, at least for arithmetic. We figure out some way to figure out enough terms so that we can fit an 11 in there, figure out how many times the 11 goes into those various numbers, subtract that away, and then sort of move over and see what happens. So what we're doing is we're subtracting off, quote unquote, the biggest parts and figuring out what's left over after every stage until there are no more parts to go through. So now we're going to apply the same principle to this polynomial. So what we're going to do is we're going to take 4x cubed minus 10x squared minus 8x plus 2 and divide it by x minus 3. So the way we do that is as we did before. So we needed to divide an 11 into a 14, I believe. And so what we needed is we had 2 digits, so we needed 2 digits. In this case, what we notice is we have 2 terms, and we need 2 terms, okay? And notice that this has 1 power of x greater than this term. This has 1 power of x greater than this term, so they're going to line up nicely. So then what we do is we figure out how many times x minus 3 goes into 4x cubed minus 10x squared. And what you do in these cases, you actually just match up the leading terms. So you need to figure out what do you multiply to x to get 4x cubed. And if you look carefully and think about it, you'll notice that you'll need 4x squared. So 4x squared times x will give us 4x cubed. And what that'll let us do is cancel off, quote unquote, the big part. So what we do is we take this and we multiply the whole thing by it. So we have 4x squared times x, so that's 4x cubed. And then 4x squared times negative 3 is negative 12x squared. All right? So we've written that down. Now what did we do? We subtracted 11 from that. So I'm going to warn you, you don't just simply put a negative sign right here because you're subtracting both the 4x squared and the negative 12x squared. And if you write the negative here, you won't distribute and you'll make a lot of errors. And sign errors will really get gnarly in a hurry. So what I like to do is I like to put parentheses around that to remind myself I'm subtracting the whole thing. And then when I distribute the negative, I just make sure I distribute it through. And then I go through and do this. So 4x cubed plus 4x, or minus 4x cubed is 0. Negative 10x squared plus 12x squared is 2x squared. And then what we're going to do next is we drop the next bit, 8x. So we repeat. So how many times does x go into 2x squared? That is 2x times. So we have 2x times x, that's 2x squared. 2x times negative 3, that's minus 6x. Put that in parentheses, subtract it. Now I distribute the negative, so I get plus minus plus. So then I have 2x squared minus 2x squared is 0, and minus 8x plus 6x, that's going to be minus 2x. Again, we drop down the 2. How many times does x go into negative 2x? That's negative 2 times. And so then negative 2 times x is negative 2x, and negative 2 times negative 3 is plus 6. Put parentheses around that, subtract it, and so then we distribute. So negative becomes a positive, positive becomes a negative. Cancels, minus 4. And since there's nothing more to drop, this is remainder negative 4. Now, just as before, this actually gives us a nice way to write down the fraction. So this is telling us that if we take 4x cubed minus 10x squared minus 8x plus 2, and we divide it by x minus 3, that'll be equal to 4x squared plus 2x minus 2, and then the remainder is negative 4 over our divisor, so that's negative 4 over x minus 3, and that gets added to the end. So what long division lets us do is it lets us rewrite this rational expression in terms of this quadratic expression and then this inverse function right here. And so this is used fairly commonly. So if you want to check if something is a 0, you try to divide by x minus that 0 to see if you get no remainder. And this is also useful for finding asymptotes on rational functions.